are going to draw the graphs for different kinds of damping. Remember, light damping is where we pull the thing down to the bottom of the screen, all the way to the bottom, we let go, and gradually over time, those oscillations become smaller and smaller. See, it started all the way at the bottom of the screen, and now it's nowhere near the bottom. But it took a while for this to happen, for that energy to be dissipated. That's light damping. On the other hand, we could turn this thing, get this thing to stop. On the other hand, instead of light damping, we could give it heavy damping, which looks like this. You pull it down to the bottom, and you let it go, and pretty rapidly it slows down. Those oscillations die off really, really quickly, and after very little time, it has almost completely stopped. So we've already seen the graph for light damping. Light damping is where the displacement over time, against time rather, the displacement against time, we start out with some amplitude, which gets smaller gradually, kind of like that. The period remains the same, and the frequency does too. Heavy damping is the same basic idea, but much more drastic. So we start out, we go something like this, and after very little time, we have come to the point where the oscillations have totally died off, after very little time. And then there are others, called critical damping and over damping. Whoops. Critical damping is where the damping is so great, you start here, that you never actually, oops, that's not very good, let me try that again. It's such great damping that you never even pass through the equilibrium position. You never pass through the center, and it kind of looks like this. In other words, it's what would happen if you pulled this mass down to like here, you let it go, and by the time it returned to the middle, it had stopped completely. And in critical damping, the system comes to rest because of that friction, that damping, in the shortest time. Shortest possible time. On the other hand, there's something called overdamping, where it starts at the maximum displacement, and instead of coming to rest in the shortest time, it comes to rest over a long time, because there's so much friction, so much damping. And in this case, just like on the other example, the system never passes through equilibrium. So those are the four kinds of damping. We have light damping, where it does pass through the equilibrium. In fact, once it passes through, it goes back down, and then it passes through again. And then it goes up, and then it passes through again, and down, through, up, down. We have the same thing with heavy damping, but we come to rest much more quickly. The damping is more extreme. And then down here, kind of altogether different examples. This friction is so great that the system never even gets through equilibrium. By the time it gets to equilibrium, it stops. So you might be wondering, what's an example, like a real-world example, of damped harmonic motion? Here is a great example. In fact, it's so great because it uses our classic spring system. This person has put a hanging spring into water, and as that spring goes up and down, it encounters much greater resistance presented by the water. And so after a very little amount of time, it goes back down to rest, and it remains at the center position. Whoops, like what you see? Okay, so anyway, let's get out of there. The idea with critical damping is that you pull the thing down, and maybe it's not in water now, it's like in bread dough or something. And it's in bread dough, the bread dough is kind of cut up, or I don't know, it's kind of doughy. So you let go, and it takes a really long time with overdamping to return back to that equilibrium position. Critical damping is the same idea as bread dough, but not as thick as bread dough. So it ends up going to the equilibrium position in the fastest time possible.